Section 3.5, multiplication and division algorithms and mental estimation. So we're not going to get to the mental estimation today. This is going to be a lot like the last section, except that we're doing it with multiplication and division instead of with addition and subtraction. And maybe I'm just a little bit partial to this section. I actually think these are much more interesting in terms of different algorithms than the addition subtraction ones were. And there's bound to be something in here that you're like, I didn't know you could do that. Isn't that interesting? And so I hope that that will be the case for you today. All right, the first thing we're going to take a look at is properties of exponents, not perhaps the most interesting thing in this section, but there are some details in this that I hope that after you look at them with me today, you can at least justify to yourself why something works. So a to the n means taking the number a and multiplying it by itself n times, okay? That's what that notation means. So there are n of these. We call the letter A, the base, we call n the exponent. And what we're going to do in this section is we're going to talk about 4 basic properties of exponents. For those of you who've had proportional statistical reasoning, this is review because we do this again there. We just go further because we need it for scientific notations, what we use it for in there. But there are 4 basic properties that we're going to see used in this section. The first one, you'll see a to the m times a to the n. And does anybody remember how to consolidate that into a to some value that's 1 power instead of 2 separate powers?
A to the m plus.
Right, we add the exponents. And what we're going to do in a minute here is I'm going to justify for you why each of these works. And again, I know some of you have seen this part before. But the second one, a to the m over a to the n. What will I do with my exponents here? I subtract them, yes. The third one, I have a to the m to the n. I multiply here. A to the m n, they're multiplied. It's not an exponent on the m, it's a multiplication times m. And then on number 4, it almost feels like this is something like a distribution property. What do you think this one changes to? Yeah, the exponent goes towards both, so a to the m, b to the m. So these are our 4 properties we're going to look at, and I'm going to justify them for you. These aren't proofs of mathematics per se, but there's some justification for why it works. Okay, so the first one that we did, we said that this should be addition. So I'm going to give you an example with numbers in it. That's why it's not a proof, because if you're doing this and you're actually wanting to prove it, you can't put numbers in to make it work. But we're going to do the example that it's a to the third times a squared. So what does a to the third mean? A 3 times, a times a times a. And what does a squared mean? A 2 times. So if we collect these now, how many a's do we have? 5. So this is a to the 5th, and how do we sort of see that we got from 3 and 2 to 5? We added them, right? So it isn't multiplication, it really is addition. We can do the same thing for this one. So this is the property, and we're going to do the example. And the example that we're going to do is a to the 4th over a to the 1st. So a to the 4th means what? A times a times a times a. And of course, a to the 1st means just 1a. This is division, right? So we can reduce common factors with division. The phrase you probably wanted to use was cancel out, right? You can cancel them out. Divide them out to 1. And I'm left with 3 a's. And again, how do I get from 4 and 1 to 3? I subtract. I subtract. Okay, I'm going to do almost the same one on 3 as what I did on 1. So this is mn. We said it should be multiplication. So the example that we're going to do is going to be a to the 3rd to the 2nd, okay? Because 3, like this property 3 and property 1, sometimes people get them confused. When do I add? When do I multiply? So a to the 3rd, of course, like you told me, means a times a times a. and this is supposed to be squared. Well, when I square things, it means that I multiply them by themselves. So this is a times a times a times a times a times a. How many a's is that? 6. And again, how do I get from 2 and 3 to 6? I multiply. The last one looked like this. And we'll do an example. It's ab to the third. Something to the third power means that I multiply it by itself 3 times, like so. And then we have the ability to rearrange this multiplication to look like this. What properties am I using when I do that? Associative and commutative. Right? Associative allows me to do the regrouping, that is move parentheses, move in and outside of parentheses. And commutative allows me to change the order, which is also pertinent in this particular case. All right, if I do that, I recognize, of course, that this is 3a's, so a cubed, and 3b's, so b cubed. Okay? So there's a very straightforward ways to justify why things are addition versus multiplication and so forth. So we're going to do just a couple of quick examples of this. If you're taking a look at part A, what am I going to do to simplify this expression? Add what? The exponents. Okay, what's the base going to be? Just 5. Don't go getting carried away. 5 is the base. It never changes. What are my exponents going to combine to? 16. 10 plus 2 plus 4, 16. Okay. Now, B is a little different. What about B makes it different than, say, A? Not all the bases are the same, and there's 2 different ways to deal with that. Okay? So I'll show you both ways to deal with it. It doesn't matter to me which one you use. They're both correct. They don't give you exactly the same answer, but the answers are related, and they're both right. That's a little weird, right? Different answers, they're both right. But they are the same value. Okay, so here's the deal. What we could do is we could take the number 6 and we could break it down. 6 is what? 2 times 3. And then we could recognize that, of course, this is 2 times 3 to the 4th. I have 2 to the 3rd, and I have 3 to the 3rd. So properties of exponents say I can write this as 2 to the 4th, 3 to the 4th, 2 to the 3rd, 3 to the 3rd. Is everybody good with that so far? What could I do next? Yeah, I can combine the ones that have the same base. So these are both 2s, so this is 2 to the 7th. And these are both 3s, so this is 3 to the 7th. So this is one way to express the answer. And when we get into chapter 4, yeah, it is chapter 4, where we do some things with factorization, this is exactly what we would be looking for. Okay, we would look for the 6 to be broken down into its prime factors. Now, this problem doesn't have to be done this way. There is another option. So from over here, what we could do is we could recognize that both of these have an exponent of 3. And so instead of trying to break the 6 apart, we can try to combine the 2 that have the same exponent together. So the 6 to the 4th stays as it was. And then this we could actually write as 2 times 3. And we could undistribute the 3. We're just using property number 4 backwards, right? We're going from left to right instead of right to left in the property. And then I have 6 to the 4th here. I have 6 to the 3rd here. And this would be 6 to the 7th. And of course, in some ways, that looks like a much cleaner representation than the other one, right? But it isn't prime, right? 6 is not a prime number. So it depends on what you're using it for. But either of those versions of this would be an acceptable answer. Is everybody good with that? So that's as much as we're going to do with exponents in this section. We'll come back to exponents more in chapter 4. Let's look at some actual algorithms now for multiplication and division. I think these are a lot of fun. All right, So the first one we're going to do is we're going to do, in fact, what we'll do is we'll do the standard algorithm, and then I'll show you what the expanded version of that looks like. So what is the standard algorithm? How in the world is it that you normally, as you have done in the past so often, do to multiply 48 times 32? Walk me through it. What do you do? 2 times 8, and what do you get? 16. And when you do 16, what do? You write down a 6 and you carry a 1. So there's sort of carrying involved, right? Then what do? 2 times 4, which is 8, and then you add. So in the middle of doing a multiplication problem, you're adding. Well, that's a little awkward, right? Think about it. You're used to doing it, but think about it. In the middle of this multiplication problem, all of a sudden you decide to add. That's a little weird. That's right, but it's weird. So what do I get, 9? Is that where I am? Okay. Then what? And then what? 3 times 8. There's something I need to do before I do that. I put a magic 0 in this place for no real good reason. I mean, no, there is really a good reason, but usually people have no real good justification for why they did it. They just know they're supposed to. That's a little weird. Okay, now I'm ready to do my 3 times my 8. We're going to talk about the whys and all this in a minute, but
I have a question.
yeah.
So do they teach us to put the 0 there? Because
Mhm.
I don't know if that's just because I.
Do you leave a blank space?
Yeah. I just left
Same
the
thing,
space.
yeah.
If I've naturally dropped it off, or if that's.
Whether you put the 0 or whether you leave it blank, you're treating it like it's a 0 in that placeholder.
So is leaving the blank space okay, or
Yeah.
is it 0?
It's fine. There's nothing wrong with it.
We always just scoot it over.
That's what the textbook does.
What's
That's what the textbook does.
the 0?
No, the blank.
The blank? It depends on the curriculum that you use as to which they will do, but either way you're doing it, the fact that you're shifting over should feel a little bit awkward to you. I mean, like the why is a little bit, usually a little bit hidden in what's going on. So let's finish this, and then I'm going to show you expanded algorithm, which will justify why we leave blank spaces or put zeros or whatever, and that'll help with that piece in a minute here. Where are we? 3 times 8, right? 3 times 8 is, we put a 4 under the 9, and now all of a sudden in the middle of the problem I'm changing a 1 to a 2, aren't I? There's a 1, now it's a 2, that's fun. And then what? 3 times 4 is 12, and then again I'm adding in the middle of my problem to give me a 14, and then when I'm all said and done I get to do some more adding in the middle of a multiplication problem. Well, at the end of it, I guess. And then I add, I've got my 6 here, I've got my 3 and I carry my 1, and I've got 1536. Okay. You are so used to and comfortable with this that it does not feel at all to you like there's anything mysterious, because you've been doing it for probably, I don't know, somebody guess for me, 10 years, 12 years, long time, right? But if you are teaching a second grader or a first grader or a third grader, wherever it is that your students hit this, how to do this, and it's the first time they've seen it, a lot of the things that we just did feel very awkward. Okay, so I'm going to show you some other algorithms that are currently in use in different textbooks, sort of prevalently, so that when you see them in your textbooks, and you'll undoubtedly see some of them somewhere, and maybe none of them somewhere too, or some of them nowhere, whatever that should have said. Yeah, it'll happen, and some of them won't. But you're familiar with them, and you go, oh, I remember what they're doing here. I remember how to do this. Or if I don't remember, at least I know how to go about figuring it out. Okay, so the expanded algorithm is a good way to justify what happened in this particular problem. So to write the expanded algorithm out is to understand that this is 40 plus 8 and 30 plus 2. And that's what those numbers actually mean, right? So you're sort of breaking them apart by place value. And then what you're doing is you're multiplying them by one another. So for instance, when you do this multiplication now, and it doesn't matter the order in which you do it, you can take the 40 times the 2, and you get what? 80. So we've got 40 times 2, and that's 80. Actually, I think I'm going to write it differently. Let me back up for a second. There's another way I've written it before. Let me start with the same way that we did before, so it mirrors what I did. How about the 2 times the 8? That's 16. Okay, so I'm going to write my 16 down. And then I'm going to write down the 2 times the 40. So what's 2 times 40? 80. So I've multiplied 2 by everything. The next thing we're going to do is we're going to multiply my 30 times 8. So what's 30 times 8? 240. Do you see where that 0 is coming into play there? Now I actually wrote it, but it's because it's multiplying by 30, agreed? And then I need 30 times 40. So what is 30 times 40? 1,200. So that's where each of those numbers is actually coming from. And then we can do all of the adding at the end. There's benefit to that, especially when kids are first learning to multiply. If they're learning to multiply and you're telling them to add in the middle of the multiplication, you're just asking yourself for them to forget when the addition happens and when the multiplication happens. This one separates the two operations, which is kind of friendly. In fact, all of the different methods I'm going to show you separate those operations. So this one's a 6. I have 1 plus 8 plus 4, which is 13. So I'm going to write down my 3 and carry. 1 plus 2 is 5, and then I've got 1536. It's the expanded algorithm. You're actually multiplying each value by what it really means instead of sort of the shortened notation for what we mean when we use the 3 in the tens place. Okay? So this is a good way of thinking about it. Even if you don't use it all the time, it at least justifies what's going on in your problem. So like when you carried the 1 a minute ago, you carried the 1 because the number was 16 and you were carrying the 1 in the tens place, and so forth. All right, partial products is actually a really nice algorithm that gives a visual to the expanded algorithm you just did. And visuals are always really good for visual learners, as you can imagine. All right? So draw a box. I want you to split your box into 4s, and I'll tell you why it's 4s here in a second. You have the number 48 and 32. So 40 is 40 plus 8, and 32 is 30 plus 2. So far, so good? Okay, so this is the reason you've got a 4x4 box, is because you have 2-digit numbers. If you did 3-digit numbers, 2 3-digit numbers, you'd have a 9-grid box, right? Because you'd have 3 digits on top, 3 digits on the side. If you have 3 digits on top and 2 on the side, you'd have a 6-grid box. It wouldn't really look like a box, it would look like a rectangle, whatever, okay? So it depends on the number of things you're multiplying together. And then each of the little boxes is the multiplication of the row and column it's on. So in order to get this box, I multiply the 40, which is the column I'm on, and the 30, which is the row I'm on. So what is 40 times 30? 1,200. And I can do this for every box. The next box is 8 times 30, which is 240. And then I have 40 times 2, which is 80. And I have 8 times 2, which is 16. Now, this is fabulous visually, and I'm going to draw you one more picture of this here in just a second too. It's not so helpful right now to have them all written in this form because adding them together is not nice and neat, right? The other form was nice and nicer and neater. So we could actually change this now over to the side and just collect our terms. This is 1,200, 240, 80, and 16. Again, I wrote them from largest to smallest. You wouldn't have to do that either, but lining them up, you have 1536. This beckons to us with our area model for multiplication. And here's why. Let's imagine that we actually drew this at least somewhat to scale. Well, 48 and 32 might look something like this. 48 is wider than 32 is long. And if I split it, I could say then that this is 40 long and this is 8 long, or wide, right? 40 wide, 8 wide. And then this is 30 long and 2 long. And you can imagine actually marking off grid marks in these boxes. I don't want to do it with the 40 and the 30 per se, because that's little 1,200 little boxes. It doesn't sound like fun to me. But you can think about it like in the 8 times 2 grid pretty easily, right? There's going to be 16 little boxes down there. 8 wide, 2 long, or however you think about it. It's going to be 16 little boxes down there. So this is the 1,200. This is the 240. This is the 80, and this is the 16. And that's why it's working for us, is because this is an area image for what multiplication is doing. Cool, right? I think that those two are the most helpful in terms of explaining what multiplication actually does. Those two models. One more model for you. It's called the lattice algorithm. It's a lot of fun. It's very clean and simple. It separates the addition and the multiplication processes and so forth. But it's not as intuitive as what's going on. So I'll explain that part of it after we're done with it. Okay, so let me just walk you through it first. Okay, so we've seen a lattice multiplication or lattice addition before. You wrote the number four, you wrote the numbers on top, and then you did this sort of grid thing underneath with these, diagonal boxes and so forth. We're going to do the same kind of thing again. We're going to write, and we don't write 40 and 8, we write 4 and 8. And again, we're going to draw a 2x2 grid box. Again, it's because I've got two two-digit numbers. There's nothing mysterious about why it's a 2x2. And I'm going to put my 32 over here on the side. So it starts out almost looking like partial products, right? I just write 4 instead of 40 and 3 instead of 30. Everybody good so far? All right, all 4 of those little grid boxes now, you need to split them with diagonals. And we're going to multiply, much like we did in the last problem, each row and column. So the first one is an 8 times a 3. 4. 4 is in the tens column, right? And 3 is in the top box over here. So I've got 4 times 3, and 4 times 3 is 12. So the tens place goes on the top, the ones place goes on the bottom. So this is 1, 2, 12. Okay? 8 times 3 is 24. 24. 4 times 2 is 8, so I only use the bottom box because I don't have a two-digit number. And then 8 times 2 is 16. So all of the multiplication is done. We're not multiplying anything else. Okay? Now what we're going to do is we're going to add, and we're going to add along columns that are on diagonals. Okay, so no longer, not columns, but we're going to add along diagonals. So we're going to extend these diagonals, if you will. Whoops, hang on a sec. Try that again. Some people like to draw them all the way out here. You can do that, or you can sort of wrap it around. It doesn't matter to me. You start in the bottom right-hand corner, though, just like with addition. So this is just a 6. I don't have to do much here. But then I need to add the next diagonal. And you don't add the 4 and the 3 and the 8 and the 2. Nothing that's on the outside adds. It's only the grid boxes inside. So don't get carried away. I'm adding 8, 1, and 4. That's it, 8, 1, and 4. 8, 1, and 4 is 13. So I'm going to write down my 3, and I'm going to carry a 1 over. Then I'm going to do the same thing. 1 plus 2 plus 2 is 5. So you can either write the 5 here, like wrapping it around, or if you've extended your red lines, kind of like I drew here, you can write the 5 down here. And then I'm going to carry my 1 down because I don't need to add anything to this, and this number is 1536. When my daughter hit 3rd grade, for whatever reason, she had a mental block with the standard algorithm for addition. And my daughter is very intelligent, or not addition, for multiplication. But that standard algorithm just was not making sense to her. She wasn't getting it. And so I showed her partial products, because that's my favorite, actually. The other one, I like the other one a little bit better. And I showed her lattice. And for whatever reason, lattice multiplication clicked for her. And she loved it. And so she did everything with lattice multiplication for quite a while. She doesn't use lattice multiplication now. She uses the standard algorithm. It's a little quicker, a little bit less writing. I mean, those kinds of things. That's fine. But for a long time, this is what clicked for her. This is how she made sense of her multiplication. So I bring that up because I want you to understand that just because you don't like one of these methods doesn't mean that it won't click for one of your students, and that could be a very helpful thing to them. And it doesn't mean they're going to do that way the rest of their life. Also, people start worrying about, well, but what about when they get into this level of math and whatever, and they're going to not know how to, that's not true. They'll figure it out. It just may not click with them right away, okay? So this method has a lot of benefits. It separates the addition and the multiplication, just like the other two. That's very friendly. What's happening when you do the carrying and when you split these diagonals is that these diagonals separated it into the right place values. So like the second place value right in here, this piece, right in here is the tens place, right? So it's the 10. This one's in the tens place because it was the number 16 already. This 8 is in the tens place because we actually had 40 times 2. That's 80. 8 in the tens place, right? So it separates it all. It's a little hidden as to what it's doing and how, which is why it's probably not my favorite because of that. I think the other methods are a lot more intuitive as to the fact of why they work. But it is very clean. It's very friendly. Okay? Are we good? That's multiplication. We really have just 2 algorithms for addition or for division. So we'll do those 2 today, and then I think the rest of it we can do next time. Okay? So let's do our 2 algorithms for division. Standard algorithm. You guys know how that works, so you're going to walk me through it. 623 divided by 5. What do I do? Okay, so you look at the value on the outside and you look at however many place values you need underneath for it to go in, right? So like if this didn't start out as 62 or 623, like the 6 at the beginning, it started out with a 4, you'd look at the 4 in the next digit, right? You look at however many you need. We just need 1 here. So how many times does 5 go into 6? 1 time, and then what do? Yeah, you multiply it times the 5 first, and then you subtract, yes. So then you have 6 minus 5, which gives you a 1, and then what do? Yeah, you bring this 2 down, so you just consider as many digits as you need. So the 12, then what? 5 goes into 12 twice. 2 times 5 is 10, and you subtract. 12 minus 10 is 2. And then what? Then we bring down the 3. 23. 5 goes into 23. 4 times. 4 times 5 is 20. And I subtract and I get a 3. How do I know I'm done? Because we're still working with whole numbers. Don't get carried away with me decimals. We will get to decimals, but that's not this class. How do we know we're done? Yeah, it's smaller than 5, right? 5 is actually a larger number than the value we have at the end. So what do we call that number? A remainder. And if we're writing our answer, at least at this age, we're usually doing something like this: 1, 2, 4, R3, right? Now, in order to do this problem, you had to know your multiplication facts. Agreed? If you didn't know that 5 times 2 was 10, you could not have done what you did. Yeah? Okay, so that's an important fact to keep in mind, is that there's this relationship of being able to do division if and only if you know how to do multiplication. And it is usually taught that way, but there is something to be aware of. So if a child is struggling with division, it may not be division at all, right? It may be multiplication that we need to go back and shore up on, okay? So something to keep in mind. Now I'm going to show you repeated subtraction. I am not telling you that this is an efficient method. In fact, it is highly inefficient. Okay, so what does efficient mean in mathematics? Well, efficient would be something that doesn't take very long, right? If you're efficient at doing something, it means you can do it fairly quickly. However, it is effective. So effective means it works. Okay? The thing that it doesn't require is you to know your multiplication facts, which is a little weird. So let me show you. All right, we're doing the same numbers, all the same thing. We are doing something called repeated subtraction. So what do? Well, our goal is to subtract multiplication by tens of the number 5. So like to subtract either the number 5 or the number 50 or the number 500 or the number 5,000. Whichever one of those is the largest that I can subtract, that's what I'm going to subtract. It's all 5 times powers of 10. Okay? So which one of those is the largest that I can subtract from 623? 500. And the way that I get 500, I'm going to write it to the side so that we're thinking through this properly. 500 is 5 times 100. It's 5 hundredths, right? 5 times 100. All right, so what is 623 minus 500? 123. Can I subtract another 500? No. But I can subtract a 50 just fine. Okay, so what is 50 though? Well, it's 5 times 10. I'll tell you what we're going to do those in a minute. Don't worry about it. Okay, we're just going to run them down for now. All right, 123 minus 50. What is that giving you? 73. So we do have to know how to subtract to use this method, obviously. It is called repeated subtraction. Can I subtract another 50? Yes. I can. So we're going to subtract one more 50, which is again 5 times 10. And I get the number 23. Can I subtract another 50? No. So now I'm down to subtracting 5. It's the last thing I can do. 23 minus 5, what does that give me? 18. And how did I get 5? Well, it's 5 times 1. Right? That's what it is. Can I subtract another 5? Yes, I can. 18 minus 5 is 13. I think somebody said 13. And again, 5 was 5 times 1. I'm running out of space, so I'm just going to continue over here. I have a 13. What am I going to subtract next? 5. Again, that's 5 times 1. So what's 13 minus 5? 8. Can I subtract another 5? Yes, I can. Again, that's 5 times 1. 8 minus 5 would be 3. Okay, so we're done again when we get a number smaller than the numbers we're able to subtract. You can't subtract 5 from 3. That gives us a negative. We're not there yet. Chapter 5. We'll get there. We're not there yet. Okay? So what's our answer? Well, the answer is how many we subtracted. We subtracted 100, 20, 1, 2, 3, 4. 124, and we had a remainder of 3. Does everybody see where the 124 came from? Now let me tell you, if I'm dividing by 5, I don't find this to be a particularly effective strategy. I don't think that's probably the most efficient thing to do. But what if you were dividing by 18? Do you know your 18 multiplication tables? I don't either. So if you were dividing by 18, and a lot of times when kids start dividing by something that's larger than what they're dealing with or comfortable with dealing with, they're doing a lot of guessing. They're saying, I think 18 will go in 5 times, and they have this scratch piece of paper where they multiply it by 5 to see. You guys know what I'm talking about, right? And they're like, oh, that was too big, and they have to try again. Oh, that was too small. I've got too much left over. I have to try again. This does eliminate some of that anyway. So there is some, benefit to doing this with the things that you don't know multiplication tables for. Or for the kids who have some learning disabilities where the memorization of multiplication tables is a particular challenge. This also has benefit, real benefit, for those of you who might be teaching special ed. Okay? Any questions on this one? Okay, so what we're going to do next time is we're going to actually take a few examples where we've got some context to them. And we're going to apply these different strategies in context. And then we're going to do some mental estimation kind of things, I believe. Yes, mental math and estimation. And then we will be finished with chapter 3. All right?